It's unfair to have to talk after Ed. I have no funny stories to tell or jokes to tell. So you have to provide your own entertainment. Okay, you're in for a tough morning then if that was funny. This is Geodynamics 4 on the topic of mixing in Earth's mantle. Mixing refers to the processes that affect the spatial distribution of composition and structure and its evolution in time. One example is illustrated here. This is a picture of a laboratory experiment done by Julio Otino and his students. We have a box filled with blue fluid, and you can generate flow inside this box by moving the boundaries. Inside this box, he immerses two blobs of fluid that's identical except for the color. Mark on the left, we have a green blob. On the right, a red one. So to initiate flow, what they do is they take the bottom boundary and move it from right to left, a fixed distance, for a certain amount of time. Then they stop the motion. Then they move the top boundary from left to right for exactly the same distance at the same speed. Okay. On the bottom is what you see after 5 periods, and then they oscillate this deformation. Top moves, bottom moves, top moves, bottom moves. And on the bottom is what you see after 5 periods of this deformation. And I think the truly remarkable thing you see here is that for some reason, and some reason that we will try and understand, this green blob is almost undeformed. In contrast, the red region has been highly stretched and has sampled a large fraction of this volume. And it's for this reason that when Julio Otino wrote this review paper, he begins the paper by writing, "Virtually everyone agrees that mixing is complicated." So we're going to spend roughly the first 2/3 of our time trying to understand this picture, how it is that mixing occurs. A couple introductory comments before I forget. If you have any questions anytime, please do interrupt and ask. I'll try and pay attention to hands going up or laptops opening, which means it's getting boring. I'll try and remember to define terminology. Jackie?
Very surprised with the red color area is really not conserved.
It looks like the area is not conserved, but there must be a little bit of diffusion going on as well, so it looks like it's getting broader. What's super remarkable about this picture, there's some symmetries there, right? I've meant to write down the equations that describe the flow. So one of my introductory things I want to mention, I'll try and remember to describe the equations that describe the system we're looking at, the boundary conditions, initial conditions, and material properties, because if I don't tell those to you, what you're looking at should make almost no sense. So here, and almost everything we'll focus on today, the Reynolds number will be very small. If you refer back to Bruce Buffett's lecture, this means the terms that he put on the left-hand side of the equations that describe inertia can be neglected. Right, so this is in the limit where viscosity dominates. It's a type of flow we call laminar. And the imposed motion is perfectly symmetric. These two blobs are symmetrically placed about the center line. Right? And despite the symmetry in this problem, we obviously end up with very asymmetric stretching. Okay, I'll try and define terminology. If I don't, just ask.
Is the Reynolds number homogeneous?
Yeah, Reynolds number is essentially 0 in this case. Okay. What do I mean by essentially 0? I think it's actually about 10 to the minus 5. So inertia plays absolutely no role in the picture you're looking at. Any other comments? Okay. So why do we study mixing? I think just about everyone who has talked so far has used the word mixing in something they said, including Ed Garnero in the previous lecture. And the goal is to try and provide a quantitative framework for interpreting geochemical measurements that we can make at Earth's surface, or structures that we can image inside the Earth, in terms of the dynamics and evolution of Earth's interior, so that we might quantify the mass and energy exchange that has occurred within the Earth. And ideally, with an understanding of mixing and the ability to make measurements, we can also say something about the nature of convection inside the Earth and its origin and evolution. So here's what we're going to cover today. We'll begin with a little bit of terminology. I'll try and explain a bit about the physics and mathematics of mixing. Talk very briefly, mostly with just one video, about mixing inside the mantle. This last topic will be anything but comprehensive. In fact, I'll show you less than Ed Garnero showed you in the previous slide. But I am happy to refer you to the posters that were up on Wednesday and that will be up again tomorrow, because they do have some beautiful examples of mixing in numerical simulations, and this is a much better introduction to state-of-the-art. Okay, so what am I going to not talk about? Bruce Buffett has already talked about convection and the equations of motion that describe these kinds of flows. We've heard many, many times about the geochemical measurements that have been interpreted and discussed already in the context of mixing. I will not talk about this third point, although it's really quite interesting, some of the numerical and computational challenges with keeping track of mixing in numerical simulations. I have just one slide at the very end to talk about what happens when the Reynolds number is no longer small, when turbulence matters. Mixing in turbulent flows is fundamentally different. And I'm also not going to talk about what happens when we have mechanically disrupted materials, as might happen, for example, after impacts. Okay. So if you fall asleep, here are the main points I'm going to try and explain today. First, flow type experienced by structures matters. Time dependence matters. Time dependence in a flow greatly enhances mixing. The properties of the material being stretched and mixed also matter. And finally, the last point is really a reminder. We'll be talking about convection and flow as an agent to cause homogenization, stirring, and mixing. But it is convection, of course, that brings material from one place to another that causes melting. Melting causes differentiation. So convection both creates and destroys heterogeneity. So I said on the previous slide, I'm not going to talk about the geochemical observations we might want to interpret. But I thought it's only fair to show maybe a couple pictures to give you a sense or remind you of the types of observations that we would like to interpret to say something about the origin and evolution of the Earth. This has been referred to a few times already. It's a histogram showing the ratio of helium-3 to helium-4 in basalts from the oceanic seafloor. Vertical axis is the number of measurements. This is an old compilation. A more modern compilation basically looks the same. What you'll notice is that samples from mid-ocean ridge basalts here in yellow have a very narrow distribution of this ratio. Ocean island basalts have a much broader distribution. Without knowing anything about what this number is telling us, one conclusion you might draw from a histogram like this is that the region being sampled by mid-ocean ridge basalts is much better mixed, much more homogeneous than that sampled by ocean island basalts. Okay. Bill showed this picture yesterday, the figure from this paper yesterday. It's a figure from Meyer and co-authors in Nature 2009. I'll explain the axes for you today. Vertical axis on the top is platinum concentration. On the bottom, it's ruthenium. These are both platinum group elements, going from 0 up to 16 parts per billion on the top. Horizontal axis is time, going from 3.6 billion years ago to 2.6 billion years ago. The data points are measurements of these platinum group elements in komatiites, so magmas that we think are produced by high degrees of melting inside the mantle. So they should be pretty good samples of the mantle. When this paper came out, I thought this was the coolest thing I'd read all year, because now we have the previous measurements I showed you were measurements made from young lavas. These are measurements made on things that erupted a long time ago, so we have a direct window into the past. And probably like so what do you notice, right? We start with low concentrations early on, right? Platinum group elements are siderophile, they should end up in the core. And we see a monotonic and secular increase over about 1 billion years, then nearly constant concentrations. The inset goes to the present day, that's Gorgona. Okay. So like many of you, when you read a paper, you probably just look at the figures first, right? And then you decide if you should actually read the text. When I saw this, I thought, oh, this is recording solidification, the basal magma ocean, slowly releasing these platinum group elements into the mantle. The interpretation of this paper is that this represents mixing of a platinum group element-rich late veneer into the mantle. I have no idea if this is right or wrong, but if it is, right, this billion-year timescale we see here can't simply be the timescale to mix stuff in or homogenize these elements inside the mantle. Why not? Well, I think it's more fundamental, and this is one of the points I'm going to try and make today, right?
Because the concentrations are all on one side?
The concentrations are all on one side, and things are varying smoothly, right? So if we release at some point in time some of these platinum group elements from the surface into the mantle, and we randomly sample the mantle, we might see some or we might not early on. So we'd expect to see lots of scatter early on, gradually trending towards a mean. And this is not something we see. So the fact that we see a single slope here in the context of mixing actually gives us two time scales, maybe, if this is the correct origin of these measurements. First, that the release time scale might be into the mantle might be about 1 billion years. The stirring time within the mantle itself could be much shorter. But again, I don't want to go into these geochemical measurements in great detail, simply to give you a flavor of the types of measurements that we would like to interpret quantitatively with understanding of the physics of mixing. Last example I just added because it came up yesterday once again was a figure also shown yesterday by Sin-T Lee and co-authors from Nature a couple of years ago. I've also added a reminder that this was an idea and paper matured here at CIDER. And since it was explained yesterday, I will not explain it in great detail again, except the idea is that early in Earth history, when the mantle's warmer, melting occurs at greater depths. And because of the higher compressibility of melts, this melt may be more dense than the rest of the mantle so that it sinks towards the base of the mantle. I should add, right, there's still melting going on here in the upper mantle, and it's these melts that erupt to the surface to make the chromatites you saw in the previous slide. Okay. And then the stuff that sinks down to the base of the mantle may be resampled by plumes later on. So here are the kinds of questions we'd like to be able to address or answer about cartoons and pictures like this in the context of understanding mixing. When do these processes happen? What are the volumes involved with these systems? And what's the entrainment rate in this rising plume of material from the base of the mantle? Okay. So how does mixing occur? There are 4 different components to mixing. We start with a box of yellow fluid into which we place a green blob. The first stage in causing mixing is to take that blob and stretch it. Okay? And because we live in a world of finite size, in order to keep stretching it, we'll see that we have to fold it so that we can stretch it again. So the first 2 stages involve a combination of stretching and folding. And the main outcome of stretching and folding is that you reduce the length scales of structures. Mixing itself also includes the process of molecular diffusion, where atoms of green stuff and yellow stuff can exchange position. And there are some systems, if we have 2 liquids and there's finite surface tension, when these length scales become small enough, surface tension forces may become important to cause a breakup of our filaments. There are other ways to cause breakup, in fact, through mechanical processes. Earth's crust is a good example. We have faults that cause mechanical breakup, and the mixing of materials that make up the crust involve breakup, but through different processes. So some definitions before trying to understand the physics and mechanics. When we talk about the expression called stirring, we're referring then to the combination of stretching and folding. And the primary effects of stretching and folding are to reduce the length scales of material surfaces. When we use the term mixing, we're referring to homogenization through a combination of the stirring process as well as molecular diffusion. So I've actually been a little bit sloppy when I've used the term mixing, at least as I've defined it here. And I'll continue to be sloppy for the most part in the next hour or so. Okay, we're also going to distinguish between the nature of the materials and substances that we're going to be mixing or stirring. When I talk about something called a passive tracer, this is a material that moves with the flow. And as it moves and is carried through the flow, it doesn't influence the flow itself. And we'll distinguish between passive tracers and what I call here active heterogeneities. Active heterogeneities are materials that have different densities, different viscosities, maybe different textures that arise from crystal deformation. And owing to these differences in property, as they move throughout the flow, they also change properties of the flow. Ed?
Does diffusion include chemical reactions?
An audience member said he had a stupid question, which was, does chemical diffusion include chemical reactions? It's not a stupid question, and I don't quite know the answer, but I would say yes. Yeah, you can think about chemical reactions because you have to bring materials in contact with each other as involving chemical diffusion. So I think you could certainly parameterize it as chemical diffusion.
Because the petrologist kind of yelled at me about a month ago about my use of the word mixing, and argued that when you have a different product from these two things coming in contact, I was just wondering how you include it.
Yeah. Well, in that context, for sure, chemical reaction is analogous to diffusion in the context of mixing, where we have a mixture of yellow and green here, right? Because we've gone from either green to either yellow. We have a different composition. And that's what a chemical reaction involves. I don't know. There are geochemists in the room who will fix anything that's wrong, right? Louise?
One thing to consider in thinking about that, it's not a trivial question, is that chemical reactions might actually increase heterogeneity, whereas the molecular diffusion that you're talking about here is going to decrease.
That's right. So Louise Kellogg is pointing out for the record that molecular diffusion is always going to decrease the concentration of green, increase the and yellow, whereas chemical reactions can produce new materials and can actually increase the concentrations of something.
One way to think about it, if you just want to say that the difference between green and yellow there are different concentrations of a rare element,
Yeah.
but everything else is the same rock, then you're just talking about diffusion. But if you're talking about different rocks, right, if the green is a slab and the yellow is permanent,
They can react with each other.
then they can only interact by having some kind of chemical reaction.
Yeah.
In addition to
So any questions about these definitions? Okay. So the first point I said I was going to make is that the nature of the flow field affects the nature of stirring and stretching. Okay. So we'll start with a little material filament, a little line element in space with some length capital Dx, and it's going to be stretched to some new length, small dx. And F is simply a tensor that describes a flow field that brings its original length to some final length. We'll characterize the magnitude of stretching by dividing the final length by the initial length. Right? So this quantity lambda is really the ratio of the final length to the initial length. Jackie the other day said that deriving equations of state is super boring. Deriving this expression right here turns out to be almost as boring. So I'm not going to show you the details because it's not too easy, actually. But it turns out that the rate at which lambda is the change in length, the rate at which the logarithm of the length changes with respect to time in a moving reference frame, capital D with respect to capital D, t, is a derivative in a moving reference frame, as Bruce Buffett defined it last time. Right? It's the partial derivative with respect to time plus u dot grad, in this case log lambda. And it scales with the rate of strain tensor denoted E, that scales with velocity gradients. M is a unit vector in the direction of the element. Okay, so I'm not going to explain and derive this, but I thought I'd give you a sense of why the rate of stretching has this functional form. Right? If you have a little element moving through space, what's going to change its length? Yeah, drag, right? And drag induces velocity gradients, right? If we had a uniform velocity, the length is not going to change, right? And so this is why we see that the expression depends on gradients of velocity. So what are we doing here? Two dots here means a double dot product. We're projecting the orientation of this deformation tensor onto the orientation of the filament. Why does orientation matter? Why does the direction of velocity gradients with respect to the filament orientation matter? Right. My arm's a filament, right? In which direction do I need velocity gradients to stretch it? If the velocity gradients were only perpendicular to it, we're not going to cause much stretching either, right? And so the actual expression here then that describes the rate of stretching depends both on the orientation of the flow with respect to the filament as well as the magnitude of velocity gradients. Okay, so to illustrate this, let's consider the simplest possible flows we can imagine that we call linear flows. And what do we mean by linear? Velocity is a linear function of space or position. Okay, and we'll consider a two-dimensional flow where the horizontal velocity v in the x direction, vx, is proportional to vertical position y multiplied by a constant g. And we'll let the velocity in the vertical direction be a linear function of horizontal position multiplied by the same constant g times an additional constant called k. What are the units of g? Per unit time, right? So it's a shear rate or a strain rate. Okay. So let's consider three n members where we're going to let k, this constant here, be either -1, 0, or 1. For the case where k is equal to -1, these are illustrated down here in the lower left. We have two types of things plotted. On the top panel are what we call streamlines. Streamlines are instantaneous snapshots of the direction of flow. And if the flow is steady, steady means does not change with respect to time. Right? A particle immersed in this flow would simply go on, that's on one of these streamlines, would follow that streamline indefinitely. Okay. So for the case when k is and on the bottom I'm showing the velocity field. The length of the arrows indicates the speed, the orientation of the arrow indicates direction. The case that's k equals -1 corresponds to solid body rotation, rotation about the point here in the middle. Is there going to be any stretching in this case? No, or if we put that little filament, right, it's just going to keep rotating around in circles. Okay, let's consider the case k equals 0. In this case, there's no velocity in the vertical direction, right? There's velocity in the horizontal direction, whose magnitude increases as you move away from the origin. Okay, so we're going to put our filament right here, and the velocity is going to carry it this way. How's the length going to increase in time? It's going to increase linearly in time for long times. Actually, I shouldn't have asked you the question. I have the answer there, right? The length lambda is going to increase linearly in time. And finally, the case where k equals -1, the horizontal and vertical velocities increase linearly with distance away from the origin, right? So the derivative of position with respect to time will scale with position. What happens when you integrate that equation? dx dt scales with x. That's just like a radioactivity equation, right? You get an exponential. And so our length lambda is going to increase exponentially in time. Okay? Which one of these three types of flows is more effective at causing stretching? Always bet on things that grow exponentially in time, like your retirement funds, right? Right? So when we start looking next at more complicated flows, right, almost all the stretching we see, ultimately almost all the mixing we see, will occur in regions that locally have flows that look like the picture in the lower right, that have extensional flows or hyperbolic flows. Linear flows cause stretching, but linear in time is much slower than exponential in time. Okay. And so this is what I mean when flow type matters, right? Most of our stretching will occur through this kind of process. Just as an aside that may come up later depending on how time goes, -1 plus 1 is equal to 0, right? So the flow in the middle, or simple shear flow, it can also be expressed as the sum of the rotation on the left plus the extension on the right. Right? And so a linear simple shear flow like this does involve reorientation, rotation, as well as stretching. Okay. So the two end members you see on the left and the right here provide the fundamental building blocks for flows that ultimately cause mixing. And these are called elliptic and hyperbolic points. So to illustrate this, again, we'll look at the result of a model flow. Again, from a paper by Julio Otino. We have a box of fluid. We let the boundary on the left move up, the boundary on the right move down. Those things we called streamlines are illustrated in the top panel for this case. Right? And so there are two locations, one on the left, one on the right, about which our flow is going to rotate. Right? We don't get good mixing around points where there's rotation. Right? And these are what are called elliptic points. There's another point in this box. There's a unique one right here in the middle, right here, where fluid on one side goes one way, fluid on the other side goes the other way. This is analogous to our local hyperbolic flow. Right? In the vicinity of that point, we have a hyperbolic flow. And these are called hyperbolic points. Okay. Yeah, Andre?
Looking at the geometry, you might think that you could get just a simple convection or rotation, like one cell in this box. Is the fact that the flows this way a consequence of the aspect ratio?
Okay, so the question Andre is asking is, in this box, why don't we get just a single right? You're basically looking at the circulation in the box. Notice both boundaries are moving. The one on the left is moving. The one on the right is moving. So absolutely, it's a consequence of the geometry of the box that we end up with this hyperbolic point in the middle.
Is that viscosity independent?
The question is, are these results viscosity independent? The Reynolds number in all these cases is so low, right, that all the flows are dominated by viscosity. Viscosity is uniform in this box, so the answer is no. Yeah. The only parameter here is the aspect ratio of the box, in fact. Yeah. Okay. So we have a hyperbolic point, which is good. We can get exponential stretching there. But this kind of steady two-dimensional flow turns out to be really bad for causing mixing. And here's why, right? If you're a fluid element sitting on one of these streamlines, what are you going to do? You're going to stay on that streamline and move around that streamline again and again and again. And where do you want to get good? Where do you find good mixing here, or good stretching? It's at that hyperbolic point. You have no way, if you're sitting here, of getting to that hyperbolic point so that you can get stretched. Picture on the bottom, what they did is they put a line of dye right here across the box, and so you can see that line of dye is being stretched and wrapped up. It simply turns out that this is a very slow way of stretching that region. Okay. So steady flows, the point here is steady flows are terrible at causing mixing and stretching. Turns out, though, the best way to cause good stretching in the system is to add a little bit of time dependence. And once you add some time dependence, you have a mechanism to allow fluid that's sitting in one place to move on to a different streamline and ultimately maybe find one of these hyperbolic points where it can start stretching exponentially. Yes?
From definition of the straight line, means these lines cannot cross each other, right?
Absolutely, right. Okay. In a steady flow, a streamline is exactly the same as a particle trajectory because the flow is not changing in time. Now, if we add some time dependence, at a given snap point in time, there'll still be streamlines, right? They indicate the direction something would be moving, right? But at the next snapshot in time, the streamlines may look different. And that'll be key. Okay, so we're going to try and understand the very first slide I showed you, the introductory slide with the yellow blob and the green blob and the red blob. Okay. So here's the model problem that was set up. We have a box. Boundary at the top and the bottom are free to move. And in particular, we're going to move the bottom boundary from right to left, a fixed distance at a fixed speed. We're then going to stop the bottom boundary from moving and then move the top boundary exactly the same distance at the same speed. This problem actually has just one dimensionless parameter once you specify the geometry of the box. It's the distance the bottom boundary moves compared to the width of the box. Okay. And it's going to be denoted with the symbol d. Later on, you'll see things plotted for a bunch of different values of d. Okay. So here's some details of the experiment that was shown on the first slide. Okay. We started with I don't have the initial conditions again. We had the yellow blob over here, the red blob over here on the right. We move the bottom boundary, then we move the top boundary. And on the top left panels, what you see after one cycle of this deformation. Right? So one thing you'll notice is the red die has been stretched out. And what's happened to the green one? It's right back where it started, right? It started here and it ended up back there. That'll be important for the next slide. Okay. 3 periods of deformation, just over 5 and 8. Notice in going from 3 to 5, right, this red die has been stretched out tremendously. Right? And the way in which you stretch things rapidly, right, is you find one of those hyperbolic points, a hyperbolic region, so you can stretch things exponentially in time. So you know that somewhere inside this region, there must be one of those hyperbolic points that the red die has experienced. Okay. But the upshot then is that in this flow, you can see there's a little elliptical region here in which things are not being stretched, they're not being stirred. So we have an unmixed region. Sometimes people call these coherent regions. And then other regions in the same flow where stretching is much more effective. Okay. Now, understanding what's happening here and more generally in flows that can vary in time and in space can be quite complicated. Right? Here we have 2 spatial dimensions, 1 time dimension. So something that's often done to help understand what you're seeing here is to reduce the dimensionality of the system by 1. Essentially, you're projecting down onto a lower order dimensional system called a Poincare section. So here we have an idealized flow. These yellow lines indicate trajectories of fluid elements inside that flow. And there's a special type of trajectory, such as this inner one here, where as it goes through one complete cycle here or orbit, it ends up exactly where it started, okay, on the surface called the Poincare section. There are other trajectories, like these other yellow ones here, that as they go around one of these orbits, they end up intersecting that surface at some different location. Okay. And these are examples of what we call, maybe obviously, non-periodic orbits. Okay. Now, remember earlier we said there's 2 types of points, right? Elliptic points about which things rotate, hyperbolic points where you get lots of stretching. There are analogous types of periodic points in these Poincare sections. This is a super busy plot, and I decided not to try and explain all the concepts here. But again, we've got a trajectory. We've got one of those Poincare sections. And the point P here is an example of a periodic point. We leave there. We come back to it again and again. Now, the key for understanding mixing is to understand what happens in the vicinity of these periodic points. And there are analogies to the hyperbolic and elliptic points you saw earlier. If nearby points move away from that periodic point over time, for example, these curves right here, this would be an example of a hyperbolic point. If, on the other hand, the non-periodic points simply rotate around the point P, this would turn out to be an example of an elliptic point. Okay. So let's return then to the flow that you just looked at, right, that caused some areas with good stretching, other areas without. Okay, that's our box here at the top. And we're going to start with the fluid element located at this point here labeled P. There are two streamlines shown here. This big loop here is the streamline for the case when the bottom boundary is moving from right to left. Right? And over the course of one cycle of this while the bottom boundary is moving, our fluid element moves from point P along the dashed line to this point labeled AN0. Okay. Is that me? That sounds like my ringtone. That was a wake-up call. Okay. So now the bottom boundary stops moving, and the top boundary starts to move, and the top boundary is moving left to right. Right. Once we change the boundary that's moving, the flow field changes. Right. The streamlines reverse. They're mirror images of each other. And the corresponding streamline that passes through that point is the smaller loop here. And over the single cycle of deformation, this fluid element moves from point AN0 all the way back to where P is located. And this is how we end up with a periodic orbit.
So the movement is periodic back and forth?
It's not back and forth, right? So this one's moving this way. The one at the top is moving that way.
Only.
Yeah, only. Right, so we're basically causing circulation around and around and around and around. But every time a different boundary moves, right, we have a mirror image of the resulting streamlines or the flow. Okay, so this is why we end up with a periodic point located right near P. And it turns out this particular periodic point, points in the vicinity rotate around it, so it turns out to be an example of an elliptic point. Right? And remember from the model problems, elliptic points, elliptic flows, rotation is not good at causing stretching. This is where the yellow dye was located that didn't get deformed. So now you can ask, well, what happens to the mirror image of that point where the red blob was located somewhere right here? In the first cycle of deformation, I don't have the streamline shown. It probably moves something like this. It ends up about there. Then the top boundary starts moving, and it gets carried along to over here, and so on. It's not able to follow one of those periodic orbits. Okay. So finally, it turns out there are other examples of periodic points inside this domain. Their locations are indicated by the stars in the picture in the lower right, and these turn out to be hyperbolic points. So in the vicinity of these hyperbolic points, in that Poincare section, you have things analogous to hyperbolic flows, and so points move away from each other exponentially fast in time. Sana? Why is the lower right asymmetric? The order in which the boundaries moves matters. So the image of across the domain of P right here only doesn't get to go all the way across before the next boundary starts to move. So if I had moved the bottom boundary right to left and the one at the top right to left, this would be the island of unmixed region, and this would be the well-mixed one. Yes?
I thought you were saying that when you construct the Poincare section, you're reducing the dimensionality of the problem. I didn't obvious from this.
Hope maybe it'll be obvious then right here. Okay. So these are examples of Poincare sections. What are the three dimensions? We have two spatial dimensions and time, 3 dimensions. And it'd be nice to look at these in a 2-dimensional plane. Okay, so this is the example we were just looking at. And basically each one of these dots is keeping track of particles in those non-periodic orbits, and they're plotted every one period, corresponding to the period of oscillation. And so the elliptic point's located right here in the middle, and then there's 3 other hyperbolic points located elsewhere. And it's in the region where we have the hyperbolic points, we get lots of good stretching, and so our fluid is able to sample all these regions with all these dots, and anything we put inside this elliptical region can rotate but does not get stretched. It has no ability to find a hyperbolic point where it can experience exponential stretching. So I don't understand this, and this is what amazes me, right? This is a super simple flow. Inertia doesn't matter. There's all kinds of great symmetries, and so you'd expect that there'd be nice patterns in what goes on. So D, again, was their one parameter. It was how far the boundaries move compared to the width of the domain. For small values of D, we have lots of islands or regions here where we don't get good mixing. Then we go up to a bigger D. We have just one left. We get to D equals 15. Everything stretches. And then we increase D again, and these unmixed regions reappear. So I have absolutely no insight into what's causing the evolution of these structures. The main upshot, though, and the importance is that you can simultaneously have some regions that stretch well and other regions that don't. Okay. So, summary of stirring. Stirring can produce complex structures and simultaneously regions that do not get well mixed. What would be nice to do is understand, of course, the circumstances under which flows produce efficient stretching of material surfaces. This turns out to be a characteristic of types of flows we call chaotic. So here's my mathematical definition of chaos. Chaotic flows are ones that have the ability to stretch and fold. I'll explain this next in a bit more detail. The trajectories of nearby tracers are sensitive to initial conditions. In fact, we've already talked about that. Remember, with our hyperbolic flow, we put 2 points very close to each other, and they separate exponentially fast in time. This is what we mean by very sensitive to initial conditions. I'm not going to talk about the gray item here because it's too mathematical for now. But one characteristic of these chaotic flows is that they can be represented with something called a horseshoe map, and I will explain this. Okay. So remember how we defined the magnitude of stretching. It was a symbol we called lambda. It was the ratio of the final length to the initial length. And we said at the time, without derivation, that the derivative, the rate of change of that material length, at least its logarithm, scale was proportional to the rate of strain tensor magnitude E. So we'll go ahead and normalize the rate of stretching by the magnitude of the rate of strain tensor and call this quantity the efficiency of a flow at causing stretching. Okay. So let's think about the efficiency of the different flows we've seen already. In a simple shear flow, right, that was the flow in the horizontal direction only, where velocity varied linearly with height. How did length increase? Linearly in time, right? What's the efficiency then of a flow that causes linear stretching? The derivative of the logarithm of t with respect to t is 1 over time, right? The derivative of the log of time with respect to time is 1 over time. So panel A corresponds to the efficiency of stretching in a simple shear flow. It decays to 0 over time. Okay. And so when the efficiency of something is 0, that's probably not good. Okay. So what was the type of flow that will have a high efficiency of stretching? That was our hyperbolic flow, right, where lengths increased exponentially in time, right, the logarithm of an exponential. This will give us a constant efficiency. So the answer to how you get efficient stretching stretching, right, is to simply have a hyperbolic flow. What's the problem with simply appealing to having a hyperbolic flow? There's a point. We're getting somewhere with this. Right. In order to keep stretching something ever faster, right, you have to keep moving away from the origin so your velocity increases linearly with distance, right? And to keep doing that, you have to move infinitely far away from your starting point to maintain that infinite rate of stretching. So, in the real world where we live in a bounded world with a finite size, the only way to continue to stretch things exponentially, right, is to find some way of bringing the fluid or material back to where you started, back to the origin, and then you stretch it exponentially again. Okay, and so we'll see, in fact, that in order to get good stretching and mixing, you need reorientation, or what I'll call later folding, so you can bring things back to the place where they're stretched exponentially fast again. I'm not sure how we're going to do for time, but there's another measure people often use besides this efficiency to characterize stretching. It's called the Lyapunov exponent. It's basically the constant in front of the time in the exponential dependence of stretching rate. So stretching rate scales exponentially in time for good mixing, and the Lyapunov exponent is a constant in front of that time. Okay. Right. Okay, so we need a combination of stretching and folding, right, to get good mixing, and this can be represented with this thing that's called a horseshoe map. It's called a horseshoe map, I think, because it looks like a horseshoe. But horseshoes don't quite look like this. I don't know why it's called a horseshoe map in reality. Here's our starting point. We have white and black. We stretch it, ideally near a hyperbolic point, so things stretch exponentially fast in time. Then we have a flow that has the ability to fold it upon itself, bring it back to the starting point where it can stretch again, and you repeat this many, many times, right? And this is our mechanism for generating very efficient stretching. But the key then is we need a combination of stretching plus folding So we need flows that have the ability to have hyperbolic points and a vehicle to bring things back to that hyperbolic point. Okay, so this is the end of point one. The point one was supposed to be that the nature of flow matters, right? There's certain types of flows that are good at causing stretching, others that are not. And to get good stretching in general, you need a combination of stretching and folding. One way to do this is through time dependence in a flow. Any questions? Barbara. You have to go back to another hyperbolic point. If you learn nothing else, maybe you've learned these words hyperbolic and elliptic points. But I think they're helpful to understand how to interpret what you see, actually. Maybe when we look at some simulations, we'll try and understand what we see in terms of these types of points. So you can go from one hyperbolic point to another, but it's only in the vicinity of those features that you get exponential stretching. Yeah. So if you get to an elliptic point, you just rotate around, and that's not so good if you want to get mixed or stretched. So the second point was that the nature of the heterogeneities being stretched also affects their stretching. And once again, we're going to consider just a couple examples of idealized model problems to illustrate how these attributes of the heterogeneity affects stretching. So here's a model problem we'll begin with. We have a box. We have a boundary at the top that moves steadily left to right, reflecting boundary conditions on the side, free slip on the bottom. The bottom panel in the upper left shows streamlines with the smooth curves, and the arrows indicate velocity directions and magnitudes. Now, inside this region, we're now going to immerse a blob with viscosity lambda mu, and the surrounding fluid has viscosity mu. And actually, I guess I'm sorry, I didn't properly appreciate this. Lambda now, we've been talking about lambda as the magnitude of stretching. Lambda means something completely different now. It's the viscosity ratio between the interior fluid and that in the surroundings. Actually, I use the term lambda here because one of our distinguished UC Santa Barbara colleagues who wrote many of the classic papers about stretching of blobs and droplets also used the symbol lambda for a viscosity ratio. Okay. So now we've introduced a different material, right, with different properties. We have a couple other boundary conditions. We have continuity of velocity and stresses across that boundary. So let's look at what happens in this system. On the bottom, you're looking at three different simulations. The closed curves that you see here represent positions and shapes of those blobs as they move through the box. Lambda is, again, the viscosity ratio. The middle case lambda equals 1 would correspond to what we called a passive tracer. So notice in the left, as you might expect, right, the more viscous blob doesn't deform too much as it circulates through this box. For the case on the right, where it's less viscous than the surroundings, notice it gets highly deformed, right? We get this long tail. Where's the stretching happening? Where's most of the stretching happening? Close to the corners. Right? Why is stretching happening close to the corners? Right, that's where the velocity gradients are. And in the context of what I've tried to explain in the previous 35 minutes, there must be a hyperbolic point, says Zach. Right? In fact, how many hyperbolic points do we have in this box? We have one in each corner, right? Yeah, and we have one elliptic point in the middle. So, anyways, the point is, right, almost all the stretching, the exponential stretching, does happen near the corners, right? In the real world, this would be near mid-ocean ridges or where plumes are sourced, and so on. Okay. There are nice scaling relations that describe the rate of stretching of these kinds of blobs, right, in terms of the viscosity ratio. Maybe actually, I will explain this one. We start with a blob. We immerse it into a hyperbolic flow or a linear shear flow. The vertical axis is the length of the blob divided by its initial radius. Horizontal axis is time. And the numbers on these curves are the viscosity ratio. So 1,000 times more viscous than the surroundings, 1,000 times less viscous. Now I've done a little trick here. I've divided the time by 1 plus the viscosity ratio. Okay. And with this normalization of time, for the most part, to within a factor of a few, the rate of stretching of all these blobs is roughly the same. So what does this mean? By dividing by 1 plus the viscosity ratio, you're simply saying or showing that the largest viscosity that's present in the system is going to dominate the stretching rate. If the blob is more viscous than the surroundings, it's the viscosity of the blob. If the blob is less viscous than the surroundings, it's the viscosity of the surroundings. Okay. Something interesting, though, happens over here on the right in a linear and simple shear flow. When the viscosity ratio is 5 and 10, do we get stretching? Things stretch, but then for some reason they decide to unstretch, right? And then they stretch and they unstretch, and they do this repeatedly. Why is that happening? There's rotation going on, right? This kind of flow, a linear simple shear flow we said earlier, we said -1 + 1 is 0. Right? This was the case where k equals 0 by reference to the earlier figure. It's a combination of stretching plus rotation. And so we're stretching our blob. It's also rotating. And as it rotates, it goes back to a new orientation and it unstretches as the flow kind of reverses relative to the shape, and then it stretches and reverses. And actually, it was shown by a guy called G.I. Taylor in 1932 that the magic viscosity ratio for this periodic deformation is 4. Okay. Last point, though, about active heterogeneities, right, was that they have different properties than their surroundings. So as they get stretched, they influence the flow itself. Last example of an idealized problem. This time we have two boundaries moving, one to the right, one to the left. Again, reflecting boundaries, free-slip surface, streamlines, and velocity field. And inside this box, we're going to put two blobs, one that's more viscous than the surroundings, one that's less viscous. And the more viscous blob kind of rotates around and doesn't do very much. The less viscous blob gets highly stretched. In fact, most of the stretching happens near the two hyperbolic points. But there's something else it does, right? Notice that we have one circulation cell on the right. We have its complement on the left, right? The flow is symmetric. This blob starts on the right, but some finite amount of it ends up in the circulation cell on the left. And the reason for this is as its presence inside the domain and as it stretches and deforms is also influencing the flow. And as these plates move, it's easier to drag fluid over this low viscosity surface here. And this breaks the symmetry of the flow you see on the top, carrying the blob with it towards the zone of divergence. But the main point of showing these three examples was to highlight the fact that the nature of heterogeneities does affect how they get stirred. And there's a secondary feedback through the flow itself. Yeah?
In your simulation, you always use the relative scale, right? Not absolute scale. But I'm not sure when in the simulation of the Mantle, what's the practical dimension that you can consider the materials to be stretched or not? Because to me, the scale like a pebble cannot be stretched. But so is there some kind of characteristic scale?
Okay, so the question is, what is the scale over which the stretching is happening? And there is no scale, right? I can put a small blob or a big blob in a fluid with a given strain rate, and its fractional change in length will be exactly the same, right? So a small pebble if a small pebble with the same properties of a big one stretches by a factor of 2, the big one will stretch by exactly a factor of 2. In fact, there was a mathematical expression that said that the stretching rate, derivative log aspect ratio, length ratio, with respect to time is scaled with the strain rate. So all that matters is the nature of the flow, not the absolute size of the object.
So is it realistic?
The question is it realistic? It's not only realistic, it's mathematically correct. Yeah.
I mean, there's some limits inside there.
That's right. So if you get to length scales that are small enough that additional physics may matter, surface tension or some other process, then undoubtedly it'll affect the flow. Matt?
So mixing terrifies me. I often want to know how we can avoid it, because there are heterogeneities
Yes.
coming up at the surface. And I'm looking at this video on the right, and there's this continuous, this preserved law with Horseshoe that will survive all the way through.
It's the hidden reservoir.
Yes. So either the model problems I showed you earlier, or this one illustrates one way in which you make regions survive longer. You make them more viscous than their surroundings. Okay, so what are we looking at now? Now we've added temperature, right? Hot bottom, cold top, so we get thermal convection. This is just like your tutorial from last time. Okay. In fact, if we didn't have the blob that's pictured on the right, we would actually get steady convection in the case on the left. Right? We'd get one plume going up the left boundary, one coming down the right, or maybe up the middle. Inside this region, Henri Samuel added a blob that's 100 times more viscous than the surroundings. And that's why it takes a long time to stretch, right? Actually, color here is composition, so more viscous, less viscous. And as that blob circulates, in fact, you may have noticed on the left that you had time dependence in that domain because the blob itself influences the flow. But to answer Matt's question, how do you make regions survive a long time? One way is you just make them really viscous, so their deformation rate is smaller. And you now know how deformation rate scales with viscosity ratio. It scales roughly like 1/1 plus the viscosity ratio.
For example, completed portions of Mantle, as their water sucked out, melting zones might survive coherently in the Mantle.
Right, so Matt is saying that if you one way to change viscosity is to remove water, which makes the viscosity higher. Okay. So, right, and you don't want temperature to counterbalance it, so the increase in temperature offsets the change in intrinsic viscosity associated with composition. Okay, so far we've only worried about differences in viscosity. Of course, you can also change densities of our what we're calling active heterogeneity. One example is illustrated here. This is a set of laboratory experiments of plumes generated above a heated surface from the work of Kumagai and co-authors. Okay, so what you're looking at the top is the results of 7 experiments, vertical slices through the plume. And they have a very clever technique of illuminating an isotemperature surface. In this case, it's something like 25.3 degrees. So on the far left, we simply have a thermal plume. And so here's a hot fluid rising vertically. Now they introduce a fluid that has a different density. It's colored orange. And to characterize the importance of the density difference, we introduce a dimensionless ratio of the compositional difference in density, delta rho x EFF, which we compare to the magnitude of the thermal buoyancy, which scales like density, coefficient of thermal expansion times the temperature difference. So this is going to tell us how important compositional buoyancy is compared to thermal buoyancy. And when this ratio is small, the case labeled B here, the dense material is really not that much more dense compared to the thermal buoyancy. And it's dragged through the middle of the plume, and the plume remains nice and symmetric. When the compositional density difference gets larger, the two cases in the middle, the dense material is carried up in the rising plume. As the plume cools, the thermal buoyancy decreases. The chemical buoyancy hasn't changed. And so the dense fluid in orange sinks back down towards the base of the mantle. And we get really complicated and ugly-looking plumes that look like seismic tomography. Okay. And then finally, in the case on the far right, we've increased the density difference to a greater extent. If the density difference is big enough, for the most part, the dense fluid stays at the base of the tank or the base of the mantle. And the entrainment of this dense fluid is in the form of these skinny filaments into the plume. And Ed Garnero in the previous talk showed nice examples of these little filaments being entrained and mixed into the mantle.
What's the light green?
What's the light green? It's all light.
The outline?
The outline, they have a way of, and I can't remember how they did this. They have a way of illuminating specific temperatures. It must be liquid crystals that fluoresce at a given temperature, right? And so they have some that fluoresce at 25.3 degrees, 31.4, 37.5. So in these experiments, they're able to illuminate 3 different isotemperature contours. That's pretty cool, actually.
In figure G, it looks like there's a higher density of those.
So the other thing I think that's going on, there's probably little tiny bubbles and impurities in here that are also reflecting and scattering light. Yeah. And that's why you can see them in the surroundings as well. Okay. And I think I made the point. Well, so at this point we have a number of options. I could show you a movie.
Show them the G.I. Taylor movie.
Okay.
Is that what you're going to show?
Yeah, I was going to show a G.I. Maybe I'll explain this picture. The G.I. Taylor movie is only somewhat related to mixing, but G.I. Taylor's kind of cool. The other option is I could take you through I can take you through a case study of a rock and see if we can try and tell a mixing story based on structures in the rock. Actually, maybe we have time to do both. I have to find it. Oh, you know the problem is? We don't have sound in here, do we?
Low Reynolds number flows are those in which inertia plays only a very small part in the conditions which determine the motion. Reynolds number for a flow which is characterized only by density and viscosity is defined as R equals LV rho over mu. Here L is a length characteristic of the field of flow, V is a characteristic velocity, rho and mu are the density and viscosity of the fluid. The numerical value...
Okay, so that was the limit we've been focusing on, low Reynolds number flows. And I'm going to skip a bunch of these demos. There's a set of experiments coming up that illustrate some of the nature and properties of low Reynolds number flows, in particular a feature called reversibility. Stokes equations are linear. And so one consequence of linear equations, if you reverse the sign of the forcing, you get exactly the opposite flow. Okay. And this should provide some background to understand the first statement on the first slide, that mixing is complicated, and why that pattern you saw was surprising.
Note its position before I start turning it. I now turn it 4 times, pushing the handle clockwise. The dye seems to mix as a drop of milk mixes when it is stirred into a cup of tea. Now I reverse the direction. And after turning exactly 4 turns, the dyed area reappears in its original position, with a little fuzziness due to molecular diffusion. To see what happens, we have a second apparatus that is filled with syrup. It has a wider gap, and we can look down on it. A little coloured syrup is injected to mark the fluid. When the cylinder is turned, this fluid is stretched round the annulus. Now the inner cylinder is turned back exactly to its starting position.
So this is a passive tracer, right?
During the forward motion, the boundary of the fluid follows a path determined at each instant by the motion of the wall. At these very low Reynolds numbers, particles within the fluid move when the boundary moves, and they stop when it stops. During the reversed motion, the boundary of the fluid retraces exactly the path it followed during its forward motion, and the particles return to their original position. The motion of a rigid body is also reversible. Here is one with a gap to mark its orientation. This is set initially in the 12 o'clock position. The motion carries the body around and also makes it rotate. On reversing, the rigid body returns to its original position and orientation. If, however, a flexible body, like this bit of yarn, is inserted, the reversal of stress will alter the shape of the body so that it will not return to its original position.
Okay. The rest of that movie is really quite good too, but not so relevant for mixing. Okay, so for the most part so far, we've been talking about two-dimensional flows. We live in a three-dimensional world. The mantle is three-dimensional. In a classic paper, V.I. Arnaud showed that steady three-dimensional flows can have chaotic streamlines. Remember the definition of chaotic from earlier, one of which is that things move away from each other exponentially fast in time. And this is possible in three-dimensional steady flows. Turns out, however, that steady, constant viscosity convection inside a spherical shell does not produce chaotic streamlines. Actually, you'll understand why on the next slide. But if we add plate motion, the story changes. So I'm going to show you just one figure to give you a sense of how and why. Actually, two. First, I'm going to tell you a little bit more about the nature of flows in 3 dimensions. And I think Bruce Buffett may talk a bit more about this on Saturday. Okay, so for flows in 3 dimensions in a spherical shell, we can subdivide the type of motion into 2 types of motion, what's called poloidal flow and toroidal flow. And here's a non-mathematical definition of these flows. Poloidal flows are flows that have no vorticity in the radial or vertical direction. So what's vorticity? Vorticity is the curl of the velocity field. And what's the curl of the velocity field? It characterizes the orientation about which things are rotating. All right, so if my hands represent 2 things immersed in a flow and the flow is doing this kind of thing, we're rotating about an axis directed through my head towards a ceiling. That would be the vorticity direction. And so a poloidal flow is one that has no rotation that involves axes directed radially from Earth's surface. And this is what the toroidal flow is. It's the flow that involves rotations in the horizontal plane. And there's surface manifestations on the Earth of these 2 types of flows. Ridges and subduction zones, ridges and trenches, for example, involve poloidal motion. Transform boundaries generate toroidal motion. And at least at the present time, the magnitude of these 2 components of our velocity field are about the same. Okay, so we'll see the significance of these 2 types of motions next in this example from Ferrachat and Yannick Ricard. So what you're looking on the top is a 3-dimensional box. It's a model problem again. We've got 2 plates. The one in the upper left moves towards the upper left. The one in the lower right moves to the lower right. We have 2 ridge segments separated by a transform boundary. Remember earlier we talked about trajectories, right, through space. And there's some that are periodic and closed, others that sample big volumes. These red ones indicate particle trajectories that follow these nice periodic orbits. If we put a little tracer particle outside this region, say over here, it can follow a much more complicated path and explore the entire volume. This would be an example of one of those chaotic trajectories. So where are we going to get good mixing? Yeah, everywhere but inside this little torus of red stuff. Picture on the lower right is an example of one of these Poincare maps. You keep track of where things go. Right? So the blue trajectories on the upper right plot with the blue dots here. And here's the region where we have an elliptical point in the middle, and we get poor mixing. So why is it that we get well-mixed and unmixed regions here? Well, again, it's hyperbolic points, once again, that cause all the stretching. And you need to get from one hyperbolic point to another. The way in which you do this is through the toroidal flow generated by plate motion, which causes a reorientation and allows you to go from one hyperbolic point to another. Okay. So plates turn out to be very effective at causing mixing as well because of their ability to rotate. And I think that's all I'll say about plates. Okay, one final point is so far we've only talked about stretching and folding. There are these 2 other components of mixing. On the far left was molecular diffusion. Do we need to worry about molecular diffusion inside the Earth? In the Earth's mantle, anyways. So let's begin with the diffusion equation written at the top. It says that the change in composition, C, with respect to time in a moving reference frame, scales with the Laplacian of the concentration. Kappa is the thermal diffusivity. Bruce Buffett showed you this equation, except C was replaced by temperature. He maybe waxed poetically about turkeys, right? And he said that the time to cook a turkey, T, scaled like its size squared. So where does this come from? Right? The term on the left-hand side looks like a compositional difference divided by a time scale. The right-hand side is a diffusivity times the same compositional difference divided by a length scale squared. We balance these terms and we find that length scales scale like the square root of time. So given diffusivities of typical species inside mantle rocks, we find that over a 4 billion year time period, right, diffusion occurs over length scales of about 1 meter. That's not very big, right? So it suggests you don't need to worry much about diffusion inside Earth's mantle. Okay. So now if we couple diffusion and advection, we can look at how they interact with each other. I'll show you one example of a calculation done by Louise Kellogg. We have a layer, we'll call it composition 1, and it's gray, immersed in something with composition 0 that's colored white. There's a hyperbolic point in the middle here, so this layer is stretching exponentially in time. In the upper right, we're plotting the concentration of the color, I guess, as a function of position across the layer for a specified strain rate or stretching rate at a bunch of different times, 350 million years at 50 million time increments, up to 500 million years. And you'll notice that finally, when the length scales become small enough, diffusion starts lowering the concentration. So how important is diffusion? The vertical axis in the bottom left is the time scale for the concentration at the center of this filament to be reduced by a factor of 2 as a function of the stretching rate for diffusivities that vary by 2 orders of magnitude. Does diffusivity matter for this time scale? It doesn't, right? We're seeing obviously the strain rate matters much more. Why is this? Stretching occurs exponentially in time, right? And diffusion scales like the square root of time. And so the exponential stretching rate dominates. On the other, but what does diffusion actually control? It controls the length scale over which the filament has to be stretched for diffusion to start to matter. Vertical axis here is the thickness of that filament at the time when diffusion starts to matter as a function of the strain rate. And we find that that length scale scales like the square root of the diffusivity, as you expect from the scaling relationships. Okay. So last topic is stretching in the mantle. How do we go about understanding now mixing, stirring in the mantle? The traditional way you would do this, of course, is to do a simulation that includes the kinds of physics you think characterize convection in the mantle. You can put in tracers, passive tracers or active heterogeneity with different properties from their surroundings, and keep track of where they go. And you can either look at these visually, you can measure various attributes of these tracers, and you can assign isotopic characteristics to them and keep track of them. Okay. And again, I said at the very beginning that I'm not going to go into this in any detail, but that state of the art is represented quite nicely, I think, in our posters that will be up tomorrow. But I did want to show you one example of a simulation because I think we can understand some of what we see in these kinds of simulations with the concepts we talked about earlier, hyperbolic points, active heterogeneities, elliptic points. This is a simulation by Brandenburg and co-authors EPSL 2008. It's a cylindrical geometry. So the geometry, how do I get this to keep repeating? Whoops. Okay, I'll define the boundary conditions, then run it just once. It was supposed to run forever, but it's 4 billion years of Earth history. Okay, free slip lower boundary. It's a 2-dimensional geometry. It's cylindrically symmetric, so the geometry goes in and out of the board indefinitely. There are 8 plates at the top. When the mantle melts, it makes this black layer, basaltic crust. The depleted lithosphere is gray. And the colors you see here indicate the time since last melting. Actually, maybe even without running the video, what features, and they make the lower mantle more viscous than the upper mantle. And finally, basalt, when it enters the lower mantle, is more dense than the surroundings. Okay, what are some of the things you notice? Upper mantle's better mixed. Now, maybe to see that, we have to actually run the simulation. So you get to see it one more time. Why is the upper mantle better mixed? Velocities are bigger in the upper mantle because it's less viscous. We've got these plates moving, creating shear. So it's a combination of higher velocities plus shear induced by plate motion. The other thing I guess you'll notice is that there's juxtaposed right next to each other things that are very young and things that are very old. There's a wide range of length scales of structures, right? There are big structures in the lower mantle, smaller structures in the upper mantle. And if you watch the video, and it's frustrating to go back and forth so many times, most of the stretching happens at these hyperbolic points where things get subducted or at the base of the mantle. What seems to be defining? Would things be different in a spherical geometry? I think so. In fact, I suspect that what you see in the upper mantle would be proportionally stretched even better because the toroidal flow becomes more effective in the upper mantle as well. Okay. So let's see. We have 15 minutes, right? Everything we've talked about so far, I'll finish early so we can get some lunch. Everything we've talked about so far has been about flow and how flow causes stretching. Now, unfortunately, when we look at observations, we don't see flow, right? We see structure, we see material. It could be geochemical measurements, it could be structure. And so the trick then is to figure out how we can relate structural measurements we can make or other measurements we can make to the type of flow. And there are a variety of ways to try and do this. Right, so the stretching efficiency, again, only characterizes the effectiveness of a flow. It says nothing about the structures that we might interpret. So we can look at structures, and we can do like Adam Zuwanski did, do spectral analysis to look at the power spectrum of variations in structure or composition. Probably the easiest thing you can do is, when you're stretching a filament, is just measure how thick the filament is. And I'll show you an example next. And try and relate the thickness distribution you see to a type of flow. But ideally, you pick some characterization of structure that allows you to distinguish between mixing processes. And if there was more time, I would have shown, maybe we'll see how it goes. So one classic example of interpreting structure in the context of mixing was Allegre and Turcotte, where they suggested that in some exposed high-temperature peridotite massifs, alternating layers of peroxenite and gray, laterite and white, represent stretched oceanic crust. Right? So it goes into the mantle with a thickness of 3 kilometers. That exponential stretching we talked about gradually reduces length scales so that we can see length scales as small as tens of centimeters. So to characterize a structure, what they do is they measure the thickness of these layers, and they count the number of layers with thickness smaller than some amount plotted on the horizontal axis. And you see a power law distribution. Right? The scale is roughly like 1 over the size. And this is kind of what you expect for exponential stretching when you introduce stuff into the mantle, right? It stretches exponentially, so you're going to find more thin layers than thicker layers. Anything to wonder about with this distribution and things we just talked about? When does diffusion start to matter? We said over length scales of, I didn't focus on the numbers and dwell on them, but it's centimeters, right? We're getting down to length scales smaller than length scales over which diffusion, in fact, should dominate the distribution. I'm not going to go into this in any detail because there are other ways to make these structures through melt segregation inside these bodies. And there are other interpretations that then don't suffer from this, seeing these small length scales. But this was the origin, for example, of saying the internal composition of the Earth has a marble cake-like structure, which I've never, to be honest, made one of these, right? But I think you have chocolate cake and white cake, and you stir them a little bit, and things stretch. But not too much. Okay. So I think I'll spend 5 minutes here to take you through a different example. And the entire point of this example will be to try and see how we can use different types of measures of structure to try and distinguish between different hypotheses about what it is that causes stretching and stirring. Okay. And rather than looking at the mantle, because it's much harder, it's hard, as we've heard many times, to get lots of measurements to characterize structure in detail, we'll look at something where the exposure is much better. This is a lava flow in Northern California. That's Mount Shasta. This is called Little Glass Mountain. It erupted 800 years ago. It's a cubic kilometer and a half of material. And if you look at this lava flow, you see structure, right? You see black bands and white bands. And these bands exist at all scales, right? There's at the field scale, the hand sample scale, that's a 1 centimeter scale bar. What you see under a microscope. In fact, the microscope is helpful here, right? Because you can see what defines the structure that you observe visually. There are little tiny crystals in here. And the bands that we see in these lavas reflect different concentrations of these little crystals. Okay. So any ideas how we make this kind of structure inside a lava flow or coming out of the Earth? I'm looking for hypotheses. We've got 2 minutes for hypotheses to be introduced, and then we're going to test them. Okay, so we have 2 different lavas that had a different history, and then how do we make bands? We stir them up, right? Okay. So we'll have some kind of convective stirring process that creates these bands. Any other ideas? These things are super viscous, right? Real viscosity is 10 to the 9, 10 to the 10 Pascal seconds. So unfortunately, it's not turbulent. So we won't test the turbulence hypothesis. Yeah, it could be shear flow in a conduit. So that, again, is a process that involves stretching, right? Okay, so we have these ideas that maybe it's convection, maybe it's stretching, that somehow produce these structures. So what we want to do is measure properties of these bands and see if we can relate them to the flow that we think did this, right? Okay. I have to guess a bit more terminology, right? There's a concept called scale invariance where the attributes you see exist at all scales, and as we zoom in and out, we see exactly the same distribution of structure. And this is a characteristic of things that we call fractals. And there's some hint that this is the case, right? We see layers at big scales, small scales, and even smaller scales that more or less look indistinguishable from each other. There's no single dominant length scale in the system. Okay, so this is characteristic of things that are fractal and have scale invariance. It turns out there's systems that are multifractal. There's not a single fractal dimension that characterizes them. And there's some processes that are called multiplicative where something acts repeatedly upon itself to produce structure. Okay. And we're going to look at these different attributes of structure and see if we can test Mark's idea that it's, for example, shear flow that's producing these bands. Okay. So let's do like what Adam Zuwanski did with seismic heterogeneity. We'll compute the power spectrum. The power spectrum measures the amount of variability of some measure as a function of the scale of that measurement. In this case, it'll be color of the bands, white, for example. Okay, so I actually don't plot length scale. I plot wave number 1 over the wavelength. And so what do we do? We take the rock and we subdivide into little pieces and simply measure the color variations and compute the power spectrum. And so we see a 1 over wave number power spectrum, right, over 4 orders of magnitude. These length scales over here are the same scale as the crystals that define the color variations. So here's one measure of structure that we'd like to relate to models. This reminds me, right, I brought some rock. So you can see what it really looks like. Okay, so here's our model for convection, right? We have some structure, right, maybe produced through degassing. We have alternating from black to white. We're going to stretch it. Maybe we're going to fold it through the convective process and do this again and again. This was the horseshoe map we talked about earlier, right? So we can make structure like this. Now, there's another piece that's being passed around, and I didn't give you the whole story when I asked you for hypotheses, but I think I have this piece being passed around. This doesn't look nice and stretched, does it? It looks like a bunch of fragments. And so another possibility that what you're seeing, right, is that for some reason the magma broke up into a bunch of pieces. They stuck back together and then were stretched, right? And so one way you make these structures is through a combination of breakage and stretching, breakage and stretching. And if you want an analogy to what this process might be, you can remind yourself of the silly putty experiment that you've done, right? Where if you stretch on silly putty fast enough, it breaks, right? And then if I put the pieces back together, I can stretch them again if I stretch them slowly, right? So maybe there's some process that operates inside our volcano where at the sides of the volcano, for example, or somewhere else, the magma's breaking, right? It's being stretched, it's breaking. The pieces are jumbled up together, right? Because they're broken up fragments. They stick back together and they get stretched again. Okay. So one way in which we can imagine doing this is to take our magma, we stretch it, we break it up into a bunch of pieces. How can I just say that?
Breaking it up, putting it back together. After this eloquent talk.
Well, if I had more time, I'd go into more detail to say how we can break it. But in fact, the analogy to silly putty is perfect. Where we apply stresses big enough that it breaks. Okay. Now, when it breaks, something really important happens. Because you're exposed to a low-pressure environment at the crack, right, water diffuses out of these liquids. This is all about volcano stuff now, so it's different. Losing that water actually produces the little crystals that make the color variations. So here we're actually coupling the breakage process with what's making the structure that we see. So this is an example of a multiplicative process where something happens that produces the measure that we're interested in characterizing. But like our silly putty, right, once you release the stresses and you stick them back together, if the stresses are low, it goes back to flowing like a liquid. Dave?
I seem to recall from a long time ago that there was some data that showed that different bands have different water contents and therefore different viscosities.
Yes. Dave's comment is that do these bands have different water concentrations? We actually do measure the water concentrations, and they vary by the highest water concentration is 0.18%, the lowest is 0.12%. In all cases, it's quite low. And I think actually that these water concentration differences are recording this breakage process and diffusion of water outside of the samples. For our purposes, though, I think the point, right, so I was going to explain a different way of, earlier we had stretching, and folding, right? That was our model for convection to produce the bands. Here what we're going to do is break these pieces, jumble them up, stick them back together, and the smaller the fragment is, the bigger we'll let the color change be. So we're going to couple what's making the scale with the color change. Okay? And there's a name given to this process. It's called the Cantor model. So here's what we do. We have real rocks at the top. Right? This could be anything. It could be geochemical measurements. It could be structural measurements inside the crust. We have all these synthetic models that we make. Right? Here's our repeated breakage and sticking back together pieces where we let the color change. This one called Baker's map. This was our repeated stretching and folding. And then we go about and characterize the statistical properties of these synthetic models. We can compute the power spectrum I showed you earlier. If you know what a fractal dimension is, you can compute the fractal dimension. You can see if they're multifractal or not. And by using multiple measures of the structures that you see, you can rule out certain of these hypotheses or models. Okay. In particular, this one here, where we had repeated stretching and folding, doesn't match the observations that you see. And this is all summarized in the table on the next slide, which I don't have time to show. So I won't.
So the thing, I guess you have two things. The thing you're breaking and then whatever is flowing in. So you have something that is, I guess, more prone to brittle failure to break. And because everything doesn't break, right? When you're saying you're breaking and getting back to the silly pipe,
Yeah.
it's within something that's flowing.
Yeah, so essentially what we're doing here is a little bit, in fact, like Earth's lithosphere in a way, or continental rocks. They can behave brittly and they can behave ductily. And we're alternating between brittle, ductile deformation of exactly the same material. One key of this model is that we break with some distribution of sizes of fragments, and that acts repeatedly upon whatever it was that we had in a pre-existing manner. So we've gone through to make the synthetic band on the right, repeated cycles of breaking, sticking back together, breaking, sticking back together.
So I guess I'm trying to visualize
Yeah.
it. If something's coming up the neck of a volcano and it's breaking, sticking back together, is happening to some component to it or all of it?
The idea here, and certainly the mathematical model, is that the entire system is going through this breaking, healing.
I mean, one of these samples that have just come out, I think the second one, looks as if one set of layers are fluidized, so they should be more viscous than the
I wouldn't use the word boudinage, but I would say that if you go back to the structure, these are the broken up fragments. They stick back together, then they get stretched out. And so simultaneously in some samples, you can see things that are broken up and very angular, some where the angular fragments have been stretched after they've stuck back together. And the hypothesis is that these long, skinny bands over here were once things like this that have just experienced more deformation.
Why do they stick back together in such nice ways?
They only look nice because you're looking at a small piece of the world. So if you go back to the very first slide I showed you with those red bands, if you look at a small little segment of that red band, all the layers are perfectly parallel to one another. But in fact, when you look at this picture, or if you look at this projected from the top down, that's what the top panel is. In fact, the layering is not quite as nice. So I want to wrap up in 1 minute, and then we can have some questions. But the point of taking you through this example was meant to be pedagogic. It's to say if you have some hypothesis about what it is that's producing structure, right, you can come up with models that predict certain types of attributes of the measurements you can make, and you can evaluate these models statistically. Do they reproduce the same statistical character that you see in your observations? So I'm going to skip a whole bunch of slides and only mention one of them to respond to something that Professor David Stevenson said earlier. Right? So everything we've talked about so far has been in the context of laminar flows, low Reynolds number flows. Much of the flows inside the Earth, in the atmosphere, the oceans, in magma oceans, has Reynolds numbers large enough that flow should become turbulent. So what is turbulence? Turbulence involves an energy cascade or transfer, as Bruce Buffett mentioned, from large scales to progressively smaller scales until viscosity starts to matter. And so now we have intermittency in space and in time. This is the Kelvin-Helmholtz instability that David Stevenson referred to. Right, we have fluid that's red on the top flowing to the right. Blue fluid is stationary relative to the fluid on the top. Small undulations in the position of this boundary give rise to pressure fluctuations that amplify the sign of those fluctuations. And so we generate large wave-like structures that have vorticity associated with them. Vorticity, again, was circulation of flow. These break up to make progressively smaller scale structures. And mixing in these kinds of flows is very efficient and very effective because we can take structure at very large scales and quickly, through this turbulence cascade, transfer the structure down to smaller scales. And as long as you get high Reynolds numbers, there are a variety of other instabilities that can produce mixing. And David Stevenson mentioned a couple of them, inertial Rayleigh-Taylor instabilities and Richtmeier-Meshkov instabilities, where density gradients are misaligned with pressure gradients. And these are all things that can only operate if the Reynolds number is high, which requires fluids. So I'm going to summarize by simply listing the main points I want to get across today, and you can read these on your own. Go ahead, please.
Go back to the slide of macroscopic picture of the rock. Yeah. Well, this rock shows no macroscopic evidence of being deformed more than once. That is my opinion. This rock has undergone more than one deformation. You would see at least micas, which are very easy to orient, to show diverse directions and orientation. And all of them are layered in this horizontal plane.
Okay, so the comment is that, or the question is, does this rock show multiple episodes of repeated deformation? This rock is a glass, so there's no micas here present. But there are little crystals. In fact, microscopically, you can look at the orientation distribution of those crystals as well. So I think there's evidence for multiple episodes of breakage and deformation here. Right? Here's an angular fragment that's not quite perfectly angular, so it's been stretched a little bit. These ones here are obviously very long and elongate. So it could be that there was a single fragmentation event that made a bunch of fragments. And for some reasons, the ones on the left were the only ones that stretched out. But this is why the point of going through these hypotheses tests, I think, is really important, because what you find is that there are systematic variations in color that scale with the thickness of these bands. And so you need some model that makes the thinner bands have more color, more crystals than the larger ones. And that's what we're trying to simulate with this set of breakage color change processes illustrated in the lower right. Right, we start with something that's uniform, break it up into a bunch of pieces, and we let the color change scale with the size of the piece. The idea being that you have more diffusion of water, you make more crystals. And then we jumble them up and do this repeatedly. If we had just a single episode of breakage, we would reproduce neither the fractal dimension, or the power law relationships we saw, or other attributes of these structures. So that really gets at the point I was trying to get across, that you want to think about the hypotheses you're trying to test and the appropriate measurements to apply to those, the appropriate analyses you apply to those measurements. Yeah.
Can I go back to the animation
Yeah, this one. I think all the figure in this pattern is the conduction. And then this thing directly goes to the lower mantle, and then the lower mantle is now well here. That means if you have really strong blue, do you still find a similar figure that the upper mantle is more mixed?
So the question is, in this simulation, the flow is looks like it's dominated by subduction, and plumes are comparatively weak. There are definitely still upwellings. Right? Mass is always conserved in these simulations. If something goes down, something else is coming up. In fact, the same mass. The plumes are much less dramatic here, but there are some plumes right here. And the plumes do cause mixing, certainly where they start, right? We have a hyperbolic point. We have good stretching there. I think you're right. So if we had the same vigor of upwellings from the bottom of the mantle here, we would see better stretching at the bottom. Surface area is different too, though.
Is it mostly internally heated?
I should know whether this is mostly internally heated or not, but I don't. Doug?
The geodynamics system optimist mine for a month ago was telling me that grain size is really important. And that if you form areas with really large grain size, their viscosity is extremely high, and then they won't mix with them. So would you agree with that kind of thing, or is that?
The comment is that grain size affects viscosity, and does that affect mixing? For sure, anything that is more viscous than the surroundings will mix or stretch more slowly.
So these simulations.
But to address whether or not you make grain size, you can make large grain sizes on relevant time scales at relevant conditions inside the lower mantle. That's a much more complicated question.
A couple of questions about this. First of all, the core looks a bit small.
Dave Ruby's commenting that the core looks a little bit small. So, Dave, there's a reason for that. Can you guess what? Why? Right, this is a 2D cylindrically symmetric geometry, so it's really to preserve the relative important sizes of the surface area.
And presumably they don't have phase transformations, which might indicate
I can't recall if they have phase transformations. For sure, though, you can tell their upper mantle is less viscous than the lower mantle.
I think if I remember this, they impose a different viscosity. I don't know if there's an endothermic base.
Yeah, the lower mantle is 30 times more viscous than the upper mantle. Everyone's hungry. How about we take one more question, and then Steve?
Can diffusivity affect viscosity? And can that make diffusivity more important than I was getting the indication?
Okay. Question is, can diffusivity affect viscosity? The process of diffusion, in fact, can affect viscosity. A good example is water. Water has a huge effect on viscosity, and water is something that can diffuse. Will it have a big effect? Probably not. At the scale in the mantle, right, diffusivities are super low. Length scales are really big. The ratio of the length scale over which diffusion operates compared to the depth of the mantle is always going to be small under any reasonable circumstance that I can imagine. Not true in magmas, though.
Can the mantle absorb a whole ocean worth of water and then spit it back out again?
Yes. So I hope everyone has a good lunch.